Good morning, everyone. So, in the previous class, we introduced ourselves to the group 14 element. And today we will start with the chemical reactivity of group 14 elements. We'll start with the reaction with the water. So in general, if we look into the group 14 elements, they are relatively very unreactive, and the reactivity increases down the group. This is a well expected fact that as you move down the group, you always expect the reactivity to increase. So that same thing is happening here as well. But if you look, if you look at this lead and try to look for its reactivity with water, it looks like a noble metal because it is quite unreactive. Even though it has a reduction potential value which is negative, which is in favor of the oxidation of lead to lead 2 plus, still you see that they are very, very unreactive. They are very, very unreactive. Now, why that is so? This unreactivity is because of the two factors that are there. One of the factors is that they quickly form coating of the oxide, that is PBO coating is formed as it reacts with water. So what happens if you react to the lead with water, as soon as this lead metal comes in contact with water, it forms lead oxide layer over it. So that prevents further reaction to happen. The second factor that is responsible for its unreactivity with water is its high over potential for the reduction of H plus to H2. So on lead surface, this reduction, that is H plus to H2, which is responsible for the reaction with water of a metal, because you know when metal reacts with water, it produces hydrogen. So that means it is the H plus reduction happening to H2. So that particular reduction has a very high over potential. That means you can consider it as a very huge hill that it has to cross in order for this reaction to happen. And because of this high over potential of the reduction of H plus to H2, again, this is another cause for the lead for being unreactive to water. Now, in general, if we talk about the various elements of group 14 and their reactivity, we find that carbon, silicon, and germanium, they are unaffected by water. However, tin, that is Sn, they react with steam to give the corresponding oxide, and the hydrogen gases evolve. And as discussed, lead is unaffected because of the protective layer of oxide layer that is formed. Also, because of the high over potential of for the reduction of H plus to H2 on the lead surface. These are the two reasons why lead is pretty unreactive towards water. So this is the reaction with water. Let's go further into the reaction with the halogens. Now, when you talk about the reaction with halogen, here we talk about the two allotropes of carbon. So when we talk about the diamond, they show no reaction to halogen. So if you react diamond with halogen, no reaction is happening. However, when you react graphite with halogen, any halogen, it forms intercalated compounds. It forms intercalated compounds. They are also called as lamellar compounds. Now, that is an important thing you have to understand, because when you talk about this is a very new type of compound, that is the intercalated compounds or lamellar compounds. I don't know whether you have heard this term before. Why there is a feasibility of intercalated compounds when you react with graphite is that if you just briefly understand the structure of graphite, usually you have hexagonal layers separated by some distance. Usually this distance is approximately 3.35 Armstrong. So if you react with either a very oxidizing agent or a reducing agent, what happens is that these type of halogen molecules get trapped inside in between the layers of the graphite. Okay, so this trapping of these molecules, these redox molecules in between the layers of these graphite lead to the formation of intercalated compounds. So that is, in between interlayer space, these small molecules get trapped. Okay, and because of the trapping of these small molecules leading to intercalated compounds, you have the space of these interlayer increased beyond 3.35 Armstrong. Often this space increases to 10 Armstrong or 6 Armstrong or 7 Armstrong because of intercalation of various molecules inside them. Now, what is the usefulness of this intercalation, if you ask me? The usefulness is that sometimes, like when the group 1 metals like potassium, rubidium, cesium, when they intercalate into the space in between these layers, what happens is that you will have these first group elements have a tendency to lose electrons. So this electron would be lost onto the electron cloud which is there on these individual layers. So thereby the conduction property of the graphite is enhanced because of that. So intercalation of various molecules can affect the properties of the graphite. Either it can increase the conductivity, or it can decrease the conductivity, or it can reduce the resistivity. A lot of things can happen with the formation of intercalated compounds, or they are also called as lamellar compounds. Now, lamellar compounds or intercalated compounds isn't possible in the case of diamond because they do not have this kind of space where these molecules can get trapped. Now, what happens is that when you react graphite with chlorine or bromine, they form intercalated compounds. And now if you ask me what is the stoichiometry of these compounds, they are non-stoichiometric compound. Usually it is very difficult to figure out the stoichiometry of these compounds. So what happens is that these halogen can get intercalated into the graphite, and these halogen have a tendency to accept electrons. So you know that on the layer you have pi cloud. So from the pi cloud, these halogens can accept the electron and thereby creating a hole in the valence band of the graphite. So now here somehow the resistivity is reduced because of the introduction of halogen by creation of a conduction due to holes in this particular intercalated compounds. So such intercalated compounds are possible where the conduction is possible because of the holes in the valence band when you react them with the halogen. However, when you react them with more reactive fluorine at this particular high temperature, what it forms is basically graphite fluorides. Now, this is slightly different from the intercalated compounds. Now, here what happens is that here, when we talk about intercalated compounds, you do not have any covalent bonding happening with the molecule and the layer. Okay. However, when you talk about graphite fluorides, what is happening is that there is a covalent bond formed between the carbon atom on the layer with the fluorine. So when this happens, what happens is that now the hexagonal rings are no more planar because it is not benzene ring now. When it forms a covalent bond, the planarity of the ring is affected and it is getting puckered, or they are changing their conformations. Okay, and this lead to these kind of covalent compounds. So whenever this reaction happens, graphite's conducting property reduces considerably because it affects the pi cloud. Now pi cloud is destroyed because of covalent bonding with the fluorine. Okay, so that has destroyed the conductivity. So when you have the formation of graphite fluorides happening, which is represented by a general formula CFN, when this happens, you have the graphite uh, conductivity being reduced. Okay, so that is how the graphites react with the halogens and form either intercalated compounds, or in the case of fluorine, they also form, apart from some intercalated compounds are also formed, but mostly it forms graphite fluorides where it involves covalent bonding with the layers, which affects the conduction property of the graphite. Talking about the reactivity of silicon with and germanium, when they react with water, they form the corresponding tetrahalides. However, when we talk about the tin and the lead reactivity, they are pretty much less reactive, because when you react them with reactive elements like fluorine, you require a little bit warming. So that's why the statement is coming like tin and lead, you will have like it's more less reactive. Right? So tin, when it reacts with chlorine or bromine in cold condition, it forms the corresponding tetrahalides. However, tin reacts with fluorine and iodine on warming to form the corresponding tetrahalides. Lead, on the other hand, they form dihalide and not tetrahalide. That can be expected because as you come in the case of lead, as we discussed in the introductory slides, that lead has a more stable oxidation state. It has +2. So that is why they preferably form a dihalide rather than a tetrahalide. Okay, so that is about the reactivity of these group 14 element with the halogen. Finally, I'd just like to talk about the slide on inert pair effect, which you already know, that in the inert pair effect, it is more pronounced in heavier elements of the group. This we discussed when we talked about the questions, right? I asked you one multiple choice question. You correctly predicted that heavier elements shows better inert pair effect. Then +4 stability decreases on descending the group. In the case of group 40, +4 is the stable oxidation state, but it decreases as you move down the group, where as you move down the group, +2 stability increases. Now, in the case of germanium and tin, the +2 oxidation, though it is found, it's not very stable. It would try to form the +4 oxidation state. So whenever you have a germanium or tin compounds present in their +2 oxidation state, they act as a reducing agent. By losing electron, they will try to acquire the +4 oxidation state. So the germanium and tin compounds in the +2 oxidation state can be act as a reducing agent. And this, in organic reaction, we use certain tin chlorides to act as a reducing agent. That reason is because the +2 oxidation state, it rather forms a +4 oxidation state because of the more stability of the +4 oxidation state in the case of tin and germanium. Now, lead in its +2 oxidation state is more ionic and more stable and more common than the lead in its +4 oxidation state. So if you have lead in their +4 oxidation state in any of the compound, they will act as oxidizing agent because they will always try to accept electron and thereby convert to the lead 2. And that is why compounds with lead in their +4 oxidation state act as oxidizing agent. Now, as the oxidation state or the valency is becoming lower, they have more ionic character. This is understood from the Fajan's rule. Fajan's rule says that as the charge or the oxidation state of an element increases, what happens? The covalency increases. So obviously the opposite of that statement is that as the oxidation state or the charge on the elements reduces, you will have it as more ionic character. So these statements you already know. I just wanted to tell you that there can be use of these germanium compounds as reducing agent and these lead compounds as oxidizing agent in various applications. So you should be aware of them as well. So that's all for the reactivity. In the next class, we will be trying to look into details of various halides as well as hydrides of group 14 element. Thank you very much for your attention.